Hello to everybody and welcome to this series of lectures which we are starting today. This is the first, actually is the kickoff lecture for this European project Strong 2020 public lecture series. I am Catalina Curceanu, researchers of Frascati National Laboratories of the INFN, Istituto Nazionale di Fisica Nucleare in Italy, and I am leading the dissemination and communication activities within this broadly international project. And I'm very happy to introduce this first lecture, which is going to be a lecture on a very, very fascinating item. How big is the proton? So as you will see, in spite of 100 years that we know about the proton, there is still some mystery related to its size. So our two invited speakers, who are really protagonists of the measurement which has finally brought to this puzzle on the proton radius, are here with us and will give us an overview of what has been done lately in this sector and which are the future activities. Before doing that, however, allow me to tell you some words about our project, because as I was telling you, this is the first lecture among a series which is starting today. So the project, it's a project which is aiming to study the strong interaction, the one which is among the quarks within proton and neutron, the one which is important for the nuclei inside our bodies, for example. This is the website of our project, so whomever is interested, please go on this link. You will find more information, you will find our activities, and you will find a lot of information of how this project has received funding from the European Union's Horizon 2020 Research and Innovation Program. Also, I want to tell you some words about us. We are about 3,000 researchers involved in these big European projects. As you might see here, we are 14 European member states, but not only these are involved in the project, there are some other states for an overall number of 36 countries participating to this effort. This project is also financing access to infrastructures, namely laboratories spread around Europe, among which Frascati is one, but that's not the only one. There are some others like COSI, MAMI, ELSA, FAIR in Germany, and CERN, which is the big lab of Europe. And also, it's a pleasure for me. You can also watch our lecture live from our webpage Strong 2020. Maybe some of you are already doing that. And with this, allow me to call into the lecture our two protagonists, which are Jan C. Bernauer and Randolf Pohl. So please, Randolf and Jan, join us and teach us about the proton radius.
Yeah, thank you very much, Catalina. And I will actually start off with something I normally don't discuss, and that's our affiliation, because I think it's quite interesting in this case. So I'm now at Stony Brook in a joint position with the RBRC, which is at BNL, where the new EIC will be built. But much of the work we will discuss here, I did as my PhD thesis in Mainz, in the Johannes Gutenberg University. And this is the place where Randolf is now as part of the PRISMA collaboration. And the work he did before was at the Max Planck Institute in Garching. So let's get going. We are talking about the proton, and the proton is really something we know about for quite some time. More than 100 years. Rutherford discovered that in 1917. And really, a couple of years later, we already knew that it's not a point particle, because Stern found that it has what is called an anomalous magnetic moment, which essentially describes that, well, we know what a point-like particle should have as a magnetic moment, and it's just different from that. And that can only be if it has internal structure, and if it has internal structure, it must have a size, right? It cannot be a point, right? You cannot have structure if you don't have an extent. So it must be some cloud, right, of particles running around. And we now know that this is described by quantum chromodynamics. And that's a really, really important theory, because essentially all visible matter is described by QCD. And it's even more, most of the mass is actually created by QCD, right? It's dynamically created by the interaction in QCD. And we want to understand that. But QCD is really hard. It's not a simple theory to solve. And the proton is the simplest stable QCD system we can have in the lab, right? You just take hydrogen gas, which is essentially protons and electrons, and you can put that in a bottle on your desk, and it will be there for 100 years, right? That's the simplest system we have. And maybe the simplest question we can ask is, how big is it? So from that, a lot of experiments were done. And the first one I want to introduce is the A1 proton form factor experiment. That was my PhD thesis, which I completed in 2010. So that's essentially one of the origins of the puzzle. But it was originally not aiming at the proton radius at all. So not at the size of the proton at all. We were actually looking at something else, what we call form factors. And they're essentially functions which describe how much the proton is not a point particle, right? So you can always calculate something assuming it's a point. And if the thing you have is different from that, you can just say, okay, that's the function which describes this difference. And we were looking at that after a series of earlier experiments by many people, because we found what looks like a bump. If you look at it in a certain angle and the right light, the data points form this bump you can see here. And we wanted to measure that bump. That was the original motivation of the experiment. With that, I go to Randolf to explain why he looked at it. Randolf?
Yeah. Thanks, Jan. So I'm the atomic physics guy. I'm not doing electron scattering as Jan does. I also started with my PhD on this project, which is even earlier than Jan did. And I'm the atomic physics guy, and we're interested in this, in the size of the proton, because the proton is at the center of the hydrogen atom, as Jan said, and atoms have a nucleus orbited by electrons. Normal nuclei consist of protons and neutrons, and hydrogen is the simplest of them all. It just has one proton, where we don't know the extension, or we want to know the extension, and an electron, which is, as far as we know, a point-like particle. So this is a cartoon of the hydrogen atom, one proton orbited by one electron, and Niels Bohr, who got the Nobel Prize nearly 100 years ago, for the explanation of the energy levels in this hydrogen atom. He could explain the energy structure of the hydrogen atom and spectroscopy done by Rydberg before. So what Bohr found, or what he postulated, is that these electrons can orbit the nucleus only on certain stable orbits. Not like planets around the sun, which can be at any distance. The electron can be only at certain stable orbits. And these orbits have different energies, and the energies are related to the photon, the color of the photon that is emitted when an electron jumps from a higher state to a lower state. Or the other way around, you can send in a photon, for example, from a laser, and excite the electron from a lower state to an upper state and absorb the photon, and then you can let the electrons jump around. So you have discrete orbits, and you have these quantum leaps where one quantum jumps up and down. And this was the beginning of modern atomic physics. Now, the hydrogen atom is really awkward. If you blow it up to the size of a Maracanã football stadium, soccer stadium, and you say this is the electron orbit, the size of the football field, then the proton is actually only the size of a pin, of a needle. And so this is really a huge distance between the electron and the proton. But still, we today are in a shape that we can measure these electron energy levels to a precision where the proton size matters. You can imagine in some picture the levels of this electron that this electron can have, like the seats around in such a football stadium. And you only have discrete positions where this electron can sit, and you can kick the electron up and down these seat rows, and That's how you can imagine in some cartoon picture an atom. Now that I've convinced you that an atom is stable orbits, then I have to tell you this is all wrong, because today we know the atom is not a planetary-like system. We have to involve quantum mechanics, and we're talking about wave functions, and we're talking about probabilities. Where can we find the electron, and with what probability? But still, and we can do wonderful theory with that, and very accurate calculations. But still, the very essence of laser spectroscopy is like I showed you in the previous slide. So these are some energy levels. In reality, they're even more complicated, and these probabilities where to find the electron are shown in these small icons here. So for these leftmost states, which are called S states because they produce sharp lines, these electrons are in a spherical position, whereas for P states, the electrons are in these dumbbell-like positions. And what you see here is that the probability to find an electron is 0 for these P states at the position of the nucleus, and it's in fact very large to find the electron at the position of the proton in hydrogen for these S states. The energy separation here we call lamp shift because Willis Lamp discovered it, and the reason for this shift of energy levels is, as we know today, quantum fluctuations of the vacuum and the size of the proton. So even though the electron is on average as far away from a needle as the first row of seats in a football stadium, the proton does have an influence on the energy levels in hydrogen. And this discovery gave rise to the development of quantum electrodynamics, which describes all what you see around you, except maybe for the radioactive decay and gravity. To scare you off how difficult this is, I will show you how you can calculate these energy levels. So what Bohr found is that the energy levels are like 1 over some number, n squared. This number is the principal quantum number. It's one of these orbits. But then Schrödinger and Dirac extended this a little bit, and then it gets really messy. You can do an expansion of this theory, and then you have to add more stuff because the proton is wiggling around, you get additional terms, and then there's relativity coming into play, and you get additional terms, and then there are these quantum fluctuation effects like self-energy, vacuum polarization, 2 photon corrections, 3 photon corrections, and this has all been calculated by an army of excellent theorists. And when you come to the very end of this equation, you see these terms which are proportional to Rp squared, where Rp stands for the radius of the proton. And that's how atomic physics is sensitive to the proton radius if theorists calculate all this tedious, huge, long equation with the required accuracy of 12 digits. And then we can do an experiment where we measure the left-hand side by laser spectroscopy. We measure the energy levels. And then, for example, we test quantum electrodynamics by seeing if these calculations give the right results. And for that, we need a proton radius. And the proton radius, that should be delivered from Jan and his electron scattering measurements.
Yes. So originally, we were not aiming to measure the radius. Until I was invited to a conference. This was actually the first time I met Randolf. And that was a conference in Venice. Well, if you look exactly, it was not on Venice. It was actually on San Servolo, which is an island in the bay there, which used to be an insane asylum for 250 years. It's maybe fitting that the physicists now meet there. And Randolf was there to talk about the non-progress in his muon experiment. And I was invited to talk about the planned scattering measurement. But it turns out that Safely Kaffenbaum, who was the organizer or co-organizer of that conference, actually had a plan in mind. He kind of had given up on Randolf. And his goal was to convince me to extend the measurement actually to also measure the radius. And that is what we did in the end. But just changing a little bit our program, we added some data points which would help to extract the radius. And to understand how this actually works, I made some animations here to maybe motivate a little bit how electron scattering can actually measure the radius. And scattering really is like playing billiards, if you look at it in a funny way. So if you just start with a table, right? You have two balls, and you shoot one ball onto the other ball. At the moment they contact, there's some momentum transfer, and the balls scatter off in two different directions, right? And that's essentially what we are doing. The only problem is, come on. The only problem is my presentation died, so I have to restart that. Give me a second. It is. Okay, sorry about that. So we were about here. So the only problem is it's a very large table. So we don't know where the particles are, right? Come on, why is it dying? It's dying all the way. It was not dying before. God. Let's do it away. These are the presentation gods. Okay, do you see this? Yes. Okay. So unfortunately, now see it. There's a header. Okay. This works better. Okay. So we don't only shoot one ball, we shoot many balls, and we don't control where they hit the ball, the target ball, right? They hit it somewhere, and we get some scattering. And depending how central we hit it, it goes off at a different angle. And we do this not only with one target ball, we do that with a lot of balls, right? We have hydrogen there, some liquid hydrogen or whatever. So there's a lot of protons, and we shoot a lot of electrons at a lot of protons. And the actual interaction is also quite different, right? So the proton is positively charged, the electron is negatively charged. So they're actually attractive. So instead of bouncing off, they do this dance where they go around each other, like it's shown here. And also the proton is not hard, right? It's a cloud of charge. And the electron, depending on its energy and where it's aiming at, can actually go into this cloud, right? So you see that the electron goes through this red cloudy thing. And we do this without seeing all of this, right? The only thing we see is in which angle the electron comes out. So we know in which angle the electron comes in because that's the electron beam we shoot at, the protons. And then we detect the electrons coming out at a certain angle. And if you do that a lot, you get statistics, right? You can, for example, measure how often does an electron come back at a certain angle. And if you tabulate this, you can make a nice graph like this. And what you see here, well, small scattering angles are more probable than large scattering angles, right? And this somehow encodes the size of this object and the distribution of the charge inside the object. And I can show you that here in this animation, where in the top half and the bottom half, there is some fictitious proton with a different size. And if I scan through the possible offsets the beam can have from that proton, you can see that I can, again, make that table. And the shape of that table is just different depending how big the proton is, right? If the proton is bigger, every time you are very close to its center, you see less of its charge, so the deflection is smaller. And if it's smaller, it's bigger, right? The deflection is bigger. So we would say here, the top one has probably a smaller radius than the distribution simulated in the lower one, right? Okay. Of course, our acoustics look a little bit different, right? We have to use accelerators, and that's the MAMI accelerator at the University of Mainz. And just to give you a little bit of an idea how this looks like, so the beam starts in the lower left corner here. We have then 2 stages of racetrack microtrons, then another stage of racetrack microtron. This is a picture of the hall. That's about, I don't know, 10 meters or so. Big machines. Mainz now has actually a 4th stage, which we didn't use for this experiment. And the beam for our experiment was just then directed here into the experimental hall of the A1 collaboration. And this is where we measured. So this is our table, if usable. And of course, the table also looks a little bit different. So that's a picture of the hall. Just for your orientation, to give you an idea of the size, this concrete block here is about a shoulder height of a normal human. The beam comes in here in this thin aluminum pipe, right? It's maybe 2 centimeters diameter or so. And the beam itself is really the thickness of a pencil tip, right? It's really, really fine beam. The target is somewhere here hidden in the middle. And you see these big things here, 3 stories high. These are our detectors, right? The holes in the billiard table, where we detect the outgoing electrons, the scattered electrons. And this ring here, you can move them around this ring here. So if you remove that black cover, it's an iron ring, and they float on an oil film. And despite being multiple 100 tons heavy, this is easy enough that you can actually do it by hand if you really have to. We have a small motor to move them around, but if you unlink that, you could actually push them by hand if they are gliding on that oil film. And then we can set different angles and measure different angles. So this is now the scary slides. I want to introduce some like nomenclature of what we measure. So this is again an example for a scattering, right? You can see that here in 3D. So the electron comes in, bounces off this now hard proton, and it goes away and is detected in some detector, right? So that detector is far away and has some extent, so it covers some angular range. And it's a 2D angular range, right? It has left, right, top, bottom. So it's what we call a solid angle. And we now can calculate or measure what part of the proton would scatter into that angle range. And that's actually, if you look in the direction of the beam, if I try to get that right, something like this, the area of the proton which you have to hit so it goes to that detector. And that area, right, it's like a cross-sectional view. And that's why we named that area cross-section. And it's the differential cross-section because it's that part of the total area which scatters into that angle. And now we can introduce these form factors. So we can calculate this cross-section for a point-like object. And I won't show you the formulas. They are really not nice. Not as bad as the ones Randolf showed you, but similar. And it doesn't matter, right? They can be calculated, and it's fine. And if the proton would be a point-like particle, that would be what it is. If you do that with something more heavy, we see that it's not that, right? Let's say we scatter off a lead atom or lead nuclei. It's different from a point-like one. And we can describe this difference by just multiplying a factor in, right? A factor which describes the form, so form factor. And because we want to have it complicated, we square it. So it's the form factor squared. For the proton, we actually end up having 2 of these form factors. One is GE and the other one is GM. One describes the electric charge configuration and one the magnetic distribution inside the proton. And they are mixed between each other depending on the energy of the electron and the scattering angle and all of this, right? But you can get these 2 form factors out. If you measure enough cross-sections, you get these form factors out. So as I said, they describe the distribution of charge, right, electric or magnetic charge inside the proton. And when we talk about the proton radius, what we actually mean is the radius or something like the radius of this charge cloud, right, of the electric charge cloud which is in the proton. So if that measures the distribution, we should be able to calculate the radius from it, right? The radius is just, one aspect of the complete distribution. And indeed, it turns out we can do that. What we need for that is the slope of this distribution, when q square is 0. What is q square? Well, that's just the measure of how much momentum you transfer to the proton, how hard you knock the proton. And you want to know that slope when there's no momentum transferred, right? So a really glancing blow, right? Then you measure the total radius of the proton. of course, you can't do that. You need to have a little bit of scattering angle to see that it actually scattered. So there's a minimum Q square you can reach. And it's a lot of the effort of many of these experiments to get that smaller. So you have to fit the data and then extrapolate to 0. So in this diagram, data starts somewhere here, right? From here and then to the right. And you have to extrapolate to 0 and the slope at 0. That is what you then converge to the radius. So we did this, or I did this as my PhD thesis, but if I say I did this, this really means the A1 collaboration did this. And I want to use this chance to thank especially Michael, Harald, and Uli, who shared me a lot there, and many more in the collaboration, and my advisors, Friedrich and Weiche, and of course also my friends and my parents, because this was a hard time, and without support you can't do this. And at the end, I would say we were quite successful. We measured 1,422 data points. And if you compare that to the complete world data set, which was in existence at that time, we have 6 times more statistical power than everybody else together. So really, really good data set. And with that, back to Randolf.
Yeah, thanks, Jan. So when we met in San Servolo for the first time, I had been working with my group already for almost not quite 10 years, but 7 years on an idea how we could add to that data set and but get a 10 times better uncertainty. So shrink these error bars, which you see here, by a factor of 10. And that could be done by a system called muonic hydrogen. I talked about hydrogen before, where you have a proton orbited by an electron. And if you take away this electron and replace it with a muon, then you get muonic hydrogen. Now, what is a muon? Muons are basically heavy electrons. Heavy means 200 times the mass. So they're really much more heavy. They were discovered by Carl Anderson in the cosmic radiation. If you stretch your hand out, you get about 1 muon per hand per second from the cosmic radiation. And a fun fact is that these muons live only for 2 microseconds, so that's 2 millionths of a second. These muons come from the outer atmosphere when charged particles from the sun hit the upper atmosphere, producing pions, which are yet other particles. But these pions then finally decay into muons, and here you see a pion decaying into a muon, and then the muon makes it to the ground. It only makes it to the ground because of special relativity, because the clock is ticking slower for this muon, and in this 2 millionths of a second where this muon lives, it travels all the distance down from the higher atmosphere to the bottom. But of course we cannot use this. We need also an accelerator to get these muons. This muon was a big problem at that time, because at that time there was a wonderful standard model. You could explain everything that we saw with protons, neutrons, and electrons. And you didn't need other particles. So when Anderson discovered the muon, famous Rabi said, "Who ordered that?" Because it messed up the whole structure of the standard model at that time. Today, of course, we know that the standard model is not only protons, electrons, and neutrons, but it's a bit more complicated, but it has a nice structure. So this is our proton. These are the up and down quarks, and lots of other quarks as well, but the valence quarks are up and down quarks. Below that, you see the electron. And here next to it, you see the fat brother, which is the muon, which has 200 times the mass. And this 200 times larger mass is exactly what we're after when we make muonic hydrogen. Because the fact that the muon has a 200 times larger mass means that the average distance between the muon and the proton is 200 times smaller compared to hydrogen. So not like in this stupid cartoon which I plotted, where you maybe have a factor of 10 or so. It's a factor of 200 where this muon is closer. And it's 200 times closer in all 3 dimensions, and that means that the muon is 200 to the 3rd power. That is 10 million times more sensitive to the size of the proton. So the muonic hydrogen is really the ideal probe for the size of the proton, if you can do laser spectroscopy on this. So of course we don't use muons from the atmosphere, as I said, and there are nice accelerators in Switzerland. Everybody knows CERN, this beautiful big accelerator where they shoot protons around, but this is not where we are. We are at an institute called Paul Scherrer Institute, PSI, which is halfway between Zurich and Basel in the northern border of Switzerland. And there's this huge experimental hall, which houses our accelerator, which is not like Jan's producing electrons, but it's accelerating protons and then producing muons from that. It's very scenic out there. This is the big hall. This is another accelerator, this time with electrons. But if you look into this big hall, you see lots of concrete that's needed against for shielding against radioactivity. And in the back, below all this concrete is our accelerator. And this is a top view. There you see all the secondary beam lines, just similar to Jan's, but our tubes have to be much larger because our beams are not as nice as Jan's. And here in this little corner out here, you see our funny shaped experiment. It goes around a corner for some peculiar reason. And this is a 5 Tesla superconducting magnet, which houses the whole experiment. Here you see a tube through which we send our laser beam from a laser hut below this concrete here. This is all a very complicated setup. This is our laser hut with lots of shiny glowing lasers. And we actually have half a dozen lasers there, all working in sync to produce the funny laser light that we need to do laser spectroscopy on this exotic muonic hydrogen atom. This is me when I was young, getting ready, closing the 5 Tesla magnet. On the right, you see my PhD supervisor and mentor, Franz Kottmann, who is supervising my screwing with these bolts, and then getting ready to do laser spectroscopy on muonic hydrogen. This is a rather complicated thing, so we have a movie that shows you what's actually happening. Here behind this concrete wall, a few meters back is the proton accelerator that produces pions, which are entering this superconducting magnet here, then going around the corner. And it's much nicer to look at the movie. So here you see this artist's view of our setup. There's a yellow pion coming in, deflected the magnetic field. Now it has decayed into a muon, and this muon is bouncing back and forth in this magnetic field through a thin disk, a thin foil, where it loses energy because we have to have very low energetic muons. And then this muon, when it's slow enough, it leaves this, what we call trap, goes around this corner that you saw in the photograph before, around guided by magnetic fields. And then entering the 5 Tesla magnet, now everything is rather quick. The muon comes in. It kicks out a bunch of electrons from very thin carbon foils. They are only a few nanometers thin. These electrons are detected. Now the laser is running. The muon goes into the target in the vessel of hydrogen. It stops there, makes a muonic hydrogen atom, and then it's struck by a laser beam and produces a signal in one of these photodetectors. Oops. This is the target, which is the heart of our setup. This is like 20 centimeters across. And here you see from the left, the muon entering. This vessel is filled with hydrogen. And then the laser beam enters here, bounces off this funny shaped mirror, goes through a hole, a half a millimeter diameter hole, which we hit from 20 meters away. And then the laser light bounces back and forth between these two mirrors. And no matter where this muon made its hydrogen atom, its exotic hydrogen, it will be hit by laser light. And we see X-rays from the de-excitation of this muonic hydrogen atom, which we record in these square-shaped detectors. That's the theory. In reality, I started my PhD thesis in '97, and we had a bunch of attempts to find this. And this is one picture from our logbook. There you want to see a bump, a really huge bump, a nice resonance peak, but we saw nothing. For 12 years, we saw nothing. And we were scratching our heads. And that's why Jan said that Savili Karstenboim on this island of San Servolo had lost faith, like probably many others, or I know that many others had lost faith in our experiment because we couldn't deliver a new value for the proton radius. But then in 2009, we did this measurement again, probably our last chance to do that. And now I show you the movie that we were watching. In reality, it was 3 weeks. I will show it to you in 90 seconds, how we found the resonance and where we found it. So this is the prediction from electron scattering before Jan measured it, and this is the prediction from hydrogen spectroscopy in 2006. And then we started to measure, and what you want to see is you want to see a peak-like structure, a Lorentzian or Gaussian peak. And the prediction, well, this guy seems to match the prediction. So maybe there's something. So this is flat line, and then maybe there's something going up. But then this peak went away. And then we found out that we are producing funny fake signals in our apparatus, producing visible light, which our X-ray detectors took for these X-rays from the muonic atom. We wrote some software to get rid of these funny pulse shapes, and then finally what's left over was this guy, just in time for a 4-day accelerator shutdown. So we were not sure if this was just yet another bad signal or if this is really the resonance which we were looking for. So we installed shields and V2 detectors, and then when the beam came back, after it did not come back very well, but when it came back after 1 weekend or so, we saw that this peak is really there, and it's going down on the other side, and we see this resonance structure that we had been looking for 12 years, but it's not where it should be. It's completely far away from the predictions, and this is was actually the reason why we didn't see anything beforehand. We were always looking in the wrong position. All the previous measurements had stopped at this point because we had expected this resonance to show up on the left-hand side here. And when we finally found it, we knew that there was a big problem going on because the peak was not where it should have been. So this is the money plot, the last plot that you saw, the money plot that we produced and which got famous. This is our observed resonance. The uncertainty is in this small bump up here. This is where the prediction was from electron scattering before Jan and the hydrogen spectroscopy. This is a calibration line which we measured, so we knew where this resonance would be. Yeah. This is physicists being excited. We had finally, after 12 years, found the resonance, and we were celebrating accordingly in the cafeteria of PSI. This is how would you imagine if physicists make a really hefty party, okay? But actually, this paper got accepted by Nature, and the Nature cover story was shrinking the proton. Which was very astonishing for everybody because our value is 10 times more precise, but it's far away from where it should have been. And the fun fact is that while Jan and I had met in 2006 on San Servolo, we met 4 years later at the same conference at this Physics of Simple Atomic Systems in Les Houches in the French Alps. Very scenic again. And I had just learned that our paper was accepted for Nature on the cover, and then I went to the lecture hall and presented our results from our Kramer collaboration, finding the small proton. And in the afternoon, Jan's supervisor presented the results from his experiment, from Jan's experiment, and it was again the large radius. So and this is this 5 standard deviations discrepancy between muonic atoms and electron scattering and hydrogen spectroscopy. So these two get 0.88 femtometers, and we get 0.84 femtometers for the radius of the proton. And this proton radius puzzle is at the heart of the discussion still today, 10 years afterwards.
So, of course, the question is, what could have gone wrong, right? Let's see what could have gone wrong on the scattering side. First, of course, the experiment itself could have had a problem, right? We always have backgrounds for scattering from other things, which we have to subtract. Other things like, is the angle we actually put the spectrometer at the right angle? Stuff like this. So are these under control? Another issue are what we call radiative corrections. So in the simple picture of the scattering, there are additional terms which we have to do calculate in theory and correct for to get back to this simple picture. And maybe there's a problem there. So that's two-photon exchange, for example. The extrapolation is a problem, right? As I explained, we can't measure at the point where we really want the slope. We can only measure at larger momentum transfers and then have to extrapolate to this point. And if you have ever done that, right, fitting is hard enough, but having to extrapolate beyond your data can introduce problems. And of course, there is the question about new physics, right? Is there something we don't know about which could produce this? And this would, of course, be great, right? This would be a nice discovery. So initially, we cross-checked the data with older data, and that showed really good agreement, right? So that's completely consistent, at least to the level of the old data. We are more precise, so it can't test us to that precision, but they are in agreement with the old data on that quality. There were some theory updates, but they do not really affect what we get out for the charge radius. It made it slightly smaller, but nothing to complain that to explain that discrepancy. It had a bigger effect on the magnetic radius, which I will not talk about much. Don't get me started on that. I will talk for 2 hours on that. But it doesn't seem to be a problem. There were tons of papers written on extrapolation, just by the fact that it's very easy to write a paper by taking somebody's data, fitting it, and then you have a paper, right? So it's very quick to do this. You don't have to set up a new experiment or anything. Some of them were very good, some of them were bad, and some were just wrong, right? But in the end, I would say the results are inconclusive. The problem is that while I believe that we did it right, the data shows some behavior if you change ranges and stuff, which are not great, where you doubt that everything is fine. So we really need data at smaller Q-squared, smaller momentum transfer, going closer to the point where we want to measure, where we want to extract the radius, to have more control over that. And a lot of papers were written about new physics. There's certainly no clear winner as, oh yes, this explains everything. So we will see. And that, in the end, we really need new data to figure out what's going on. Back to you, Randolf.
This is a picture from a conference, yet another conference in 2012 in Trento, in Italy. It's all in Italy. And you see Jan and myself, still a bit younger then.
And obviously pre-COVID.
And I co-organized this with Ron Gilman and Jerry Miller, these two gentlemen here in the front. And there you see Aldo Antonini, who is my colleague in the Muonic experiment, and Franz Kottmann, my PhD supervisor, and also in the Muonic experiment, and lots of good friends. And we had 47 people coming there from theory and experiment, from atomic physics, from nuclear physics, from particle physics, from electron scattering, and from this beyond standard model physics. So ideas how one could extend this beautiful standard model to find to explain unexplained phenomena like this discrepancy in the proton radius. We had nearly 40 talks. We had what we call fighting sessions, where people would make provocative remarks, and then everybody was discussing how this could be and so on. But in the end, after this whole week in Trento, the conclusion was we have to vote, because it was not obviously clear what could be wrong. And the vote said it's probably a problem in any of the measurements. And what Jan just said is we need more data. So what is there on the more data side? We had follow-up conferences every 2 years in Mainz and Trento. And people got interested in this problem, in this proton radius problem, and started their own projects like electron scattering. Here's Ershad Gasparian, for example. By the way, this is Savelli Karstenbaum, the guy who invited Jan and me to San Servolo in Venice. He's the Russian theorist who got this all started. And there's lots of people who actually did their own experiments. And now, a bunch of years later, we are now getting the data in, because these experiments typically take like 10 years or so on the order of magnitude, because any serious experiment really needs a lot of time for preparation, for taking the experiment, and for analyzing the data. Some of the attempts that were ventilated to explain the discrepancy between the two proton radius measurements is there's a measurement problem either in our muonic measurement or a freak coincidence between a hydrogen problem in hydrogen spectroscopy and in electron scattering. It could be a theory error. I didn't talk about this crazy long theory expression that I showed you for hydrogen. Looks much simpler for muonic hydrogen, where an energy difference that we measure is related to the proton radius by this simple, innocently looking formula. In detail, it's more complicated. But if there was a problem in this formula, then from our measurement, you would extract a wrong radius. Or it could be a problem in the standard model of particle physics, something that we didn't think about, or a new particle or new force. Some of the early ideas were, for example, the charge distribution of the proton looks different. So if you assume the proton is this, funny, fuzzy charge distribution, and if it had a halo, a long-range charge getting very far out in the tails of this distribution, that could explain the discrepancy, because with muonic atoms we would just simply probe this much more, whereas electrons would probe this much more. But this is against the other measurements in electron scattering, where you extract from the form factors that Jan introduced you. You determine a so-called third Seemach moment, and that is clearly against this halo hypothesis. Then it could be that the muon modifies the proton. You all know the tides on Earth, where the moon pulls on the Earth and makes the tides. The same happens actually when the muon is very close to the proton. It twists the proton and we call it polarizes it. And for the expert, this is the proton polarizability, but it's much too small, and it's considered. And for the experts, these are the Feynman diagrams, where this is the normal interaction between a muon exchanging a photon with a proton. Here's this form factor blob, and you can have other ways for the muon to exchange information with the proton. And this is included. But then it could, of course, also be a new particle, because we have big problems in our standard model. Gravity has no place in the standard model. There's dark matter, and we have no candidate yet that could explain dark matter, and nothing in the standard model can take account of the dark matter. There's the dark energy, where we have no clue at all what this is. It's also not included in the standard model. We don't know. We cannot explain why we're here, because we shouldn't be here, because there shouldn't be enough protons for us to build us, and other problems. And so there's lots of room for new physics. But before you ascribe some funny discrepancy to new physics, you have to check. You need new data and check for errors in the existing measurements. And now, Jan.
Okay, so finally we got some new data. So the first experiment was actually, again, an experiment in Mainz using initial state radiation. So as I said, the problem, or one of the problems, is this extrapolation. You want to go to lower q squared, to lower momentum transfer, to measure that better. And you're normally limited by two factors: the minimum angle you can measure at, right? If you measure more forward, you need smaller momentum transfer to get the electron to that angle, and by the minimum energy of your beam, and which has a limit in Mainz by 180 MeV, mega electron volt. So, and the idea was, well, we could actually lose some of that energy if the electron sends out a photon before it scatters. And it does that with some probability before the scattering process. And that's part of the normal radiative corrections. But you can turn that around and use this to measure at lower momentum transfer. And that's what we did. Miha did this and analyzed this very carefully. And the first good news is the radiative corrections seem to be good to at least 1%, which should be good enough. And the result we got out for the radius is actually something which is compatible with the large radius, right? So the typical large radius, what we had is 0.875, something like that. So that's very close to that. But our precision is not good enough to really reject the smaller one. So that could also be the smaller one, and it just scattered large in this case, right? So it's not a definitive result in any sense. And we hope that we can redo this in the future with the things we learned how to do this. The other big experiment, or the big experiment which came out recently, is PRAD. That was an experiment at Jefferson Lab. And they went the other way. So they actually had larger beam energies. They measured at 1 giga-electron volt and 2 giga-electron volts. But they went to very small scattering angles. So the target is around here, and the detector is here. And I think this is something like 6 meters or so. So it's very small angles. It's few degrees where they measure the scattering. And what they got out was a small radius. It's actually slightly smaller than the muon radius. And so this strongly prefers the small radius. But it only marginally rejects the large radius if you take the errors into account. if you just take this alone, you would say, okay, it's probably not the large radius, but it could also be a fluke. But it's going to the small radius for sure. So does PRAD actually resolve everything? Well, it turns out I don't think it does. So it's not that the PRAD, which measured mainly the clue square, okay, it's the different extrapolation, and then it's the small radius. And I tried to illustrate that here. So this line is a fit to all the data before Mainz, right? This is the Mainz data. And you can see, well, there is some discrepancy here at the right side, but it's within our understanding of how good the data was for the green line and all of this. And it's very good agreement here, right? And the radius is at the left edge. You can now take a calculation of how the proton form factor should look like if it is the small radius. That would be the blue line. Or you can say, okay, if it's the extrapolation in the Mainz data, I just force the radius to be this value and fit everything else. And then you get the magenta line, right? You can see this is somewhat close to this data and maybe not so close to this data, but it has this downward slope. If you now plot the PRAD data on top of this, there's a clear discrepancy, right? So most of that data is here, but where we don't have overlap, right, where we can't say anything how good it fits to the old data, but where we have overlap in that Q-square range, these points are not on top of these points, right? So, and also not on top of the green line. So either PRAD is correct and all the old data is incorrect, or there is a problem somewhere, right? Cannot be correct both at the same time. Which, if PRAD is correct, would mean that all the form factor data we have, right, even at larger Q square, which goes to tens of Q square, right, in these units, is maybe wrong, right, if we don't understand this discrepancy. So we still, with PRAD, I think we need more data. We need to understand this discrepancy. Which brings me back to Randolf.
Yeah. Sorry. Yes. So we also did new measurements, and here you see the proton radius puzzle as it showed itself at this magic conference, and ever since until 2014. So we had the Munich hydrogen measurements on the left side, 8.84 femtometers, and all the previous electronic measurements. And the Munich deuterium, which was our next measurement, we measured the deuteron, and by some magic you can, from the deuteron charge radius, determine the proton charge radius. This also agreed with the smaller proton radius hypothesis. But then a flurry of other experiments came in from hydrogen spectroscopy in the last, maybe say, 3 years. One in Garching, which I contributed to, was the first measurement from normal hydrogen, which also got the small charge radius. And then everybody thought that, okay, it looks like there's no problem in atomic spectroscopy. But then half a year later, another experiment came out, which again claimed the large radius from normal hydrogen. And then there was an experiment from Toronto, which again showed the small radius. So there's clearly some excessive scatter, and we clearly seem to not understand something in the uncertainties or in the systematics that determine the position. Then, if I finish this now, this is the measurement from PRAD that Jan just talked about, which favors the small radius, but has also only 3 sigmas or so away the large radius. And an update of this recent measurement from Paris just appeared, say 3 weeks ago or so, from Garching, where we measured the same transition. This 1s/3s transition in normal hydrogen, and that gave also something like the small radius, but it's not quite in agreement with where it should be. So there may be still some problem with theory or some systematic error that was not taken care of correctly. And now Jan.
So for scattering, there are more experiments in the pipeline. And Mainz, again, is doing a lot of that. So essentially, there's an updated version of the original Mainz experiment in planning and being conducted right now, where we essentially try to improve on all the things which have gone wrong in the original experiment. Right? If you do these kinds of experiments, you learn a lot what not to do, and you can do better next time. And one thing which is a big improvement is our target. Right? So in the original experiment, we used liquid hydrogen. So we cool down hydrogen until it's liquid, and it's essentially in a like cigar-shaped metal container, and the beam goes through that. So some of the beam will scatter off the metal instead of the hydrogen. That gives us background we have to subtract. We go now to a hydrogen cluster jet target. What is this? Well, you see it here on the right. It's essentially a nozzle where you push hydrogen through at really high pressures at low temperatures. So it's a gas jet, and around that is vacuum. So it's a gas jet in vacuum, which expands in what is called a Laval nozzle, cools down through the expansion, and builds clusters of crystals of frozen hydrogen, which then just fly through vacuum until they are collected in the catcher. That's the cone below that. You can't do this for much length, but you can do it for a couple of millimeters, just enough that you can send the beam through. So you have now first a point light target, which helps, and there's no background because you only go through vacuum and hydrogen. That has been built by the Münster group, and it's now in testing in the A1 collaboration. And right now we have an experiment essentially aimed to cross-check the PRAD data in the overlap with the old data. So it's only one energy. Using this new target, it's a PhD grad student from MIT, Yimin Wang, who does this with me. And finally, this experiment or this target will be the workhorse target for the MAGICS experiment, which is essentially the A1 successor for the new accelerator Mainz is building called MESA, which is an energy recovering accelerator. This is here the floor plan. There are many, many different experiments. And one of the experimental sites is called MAGICS. And there we want to do another proton radius experiment. And the specialty of that is we can also take data which is really sensitive to the magnetic radius, which is not covered by any other experiment, really. So something to look out for in the next 5 years or so. There are more. Mainz is also using a hydrogen time projection chamber, which is a type of detector. But the detector itself is also the target because it's high pressure hydrogen in that detector, which acts as a detection, but also as a target, and they are measuring the recoiling proton. So it's a completely different type of measurement, different systematics. So it will hopefully help to understand this. There's an experiment in Japan, so it's not only Mainz, for really ultra low Q square. And PRAD 2 is in the works, which is an updated version of the PRAD experiment at Jefferson Lab. And they got the green light at the last advisory committee. So these are all electron experiments. And if you think about it, originally the puzzle was not between atomic spectroscopy and scattering, but between muons and everybody else. So we had muons spectroscopy, we had electron spectroscopy, and electron scattering. But we never had muon scattering at a precision where we could extract the radius. And there are now 2 experiments which will address this. And muon scattering has other benefits. For example, the radiative corrections are smaller. So there are 2 experiments to address this. One is called AMBER. This is the successor of an earlier experiment called COMPASS at CERN. And one part of that experimental program is to measure the proton radius with muons. They just got the green light a week ago, so they will take data next year, hopefully. So it's something to look out for. And then there's MUSE. This is the muon scattering experiment at PSI in Switzerland. And as I'm part of that, I want to talk about that a little bit more. So Randolf already introduced PSI, and PSI is really special in the world because it's really the most powerful low energy electron pion muon beam. And we will actually make use of all 3 of these species in both charge types, right? So positrons, electrons, pi plus, pi minus, mu plus, pi minus. And we measure all 3 species at the same time. And by just changing the magnet polarities of the channel, we can switch the polarity of the particle with the same setup. So a lot of systematics cancel in these comparisons. So we get really excellent control and can say, yes, the muon scatters the same way as the electron. And between the two charges, we can correct radiative corrections better. So that's one of the NSF flagship experiments, and Muons is largely funded by them, and I'm too. So it's a little bit special because the beam is not so nice. It's a really wide beam. And so we have to track actually every incoming particle. We cannot rely that it's in this fine beam. And because the flux, the beam current is so low, we have to have really large detectors and cover large angular acceptance. So we have really large detectors around the target and no magnets or anything like this, which would produce this. The other problem of this experiment is because the beam is mixed, right? There are all three species in there, and mostly it's dominantly pions, which we are actually not that interested in. We actually have to make sure that we only take data, or predominantly take data, if it was a muon or an electron. So we have to do this particle ID while we do the experiment, right? While we take data, so that we not only take pion data, because there's a limit from that. Okay, back to Randolf.
Yeah, so this is the plot that I showed you before. This is the spectroscopy side, and the interesting thing is from all the people that you saw in these conferences before, I mean, lots of them have started their own projects, and there's many more things are coming in the pipeline. So just yesterday, I wrote a referee report for a PhD thesis that extends on this 2s4p measurement by measuring 2s6p in hydrogen. Then there are measurements from Paris measuring 1s4s, and we're looking into deuterons. Then people are looking into exotic muonic systems where you have a muon and an electron, where you can test quantum electrodynamics without the problem of a proton size. We have just submitted a paper that determines the helium charge radius from muonic helium. There are people who are measuring complementary things, the Ripper constant that I did not introduce you on the first slide with this complicated formula, which is tightly connected to the proton radius. So there's a whole wealth of experiments, and that is maybe the main point of all this discrepancy. No matter what the outcome will be, it has sparked so many new, exciting new measurements, and we've learned so much about electron scattering, about properties of the proton, about laser spectroscopy, about fundamental constants. We've improved fundamental constants by some factors in the meantime. So that is an exciting thing, and for the years to come, we will have new results on this. I would argue that the proton radius puzzle is, even though the most recent measurements start to lean towards the small muonic proton radius, it's still not solved because we don't understand what may have gone wrong in the previous hydrogen spectroscopy measurements, for example. There's still a chance that the muon wants to tell us something exciting. There are other experiments which see discrepancies when you look at the muon, which we didn't talk about today. So maybe there's really some new physics showing up with the muons, and it should show up with muons. There are some people who expect that. It could be a freaky measurement error, and no matter what, we will learn something from that. It has, as I said, motivated lots of new measurements. One of them, and lots of interesting events like the one today, where we can talk about the proton problem. I would like to take this opportunity to talk to thank my colleagues in the muonic experiment. This is a slide which is maybe 10 years old or so. And if you want to read about stuff that Jan and I did until 2014 when we wrote this paper, and what we planned at that time, and compared to what we told you today, what we did since then, you can read in any language you like one of the articles that we wrote together 6 years ago. Thanks a lot.
Actually, I also have a slide. I have a final slide. So from the scattering side, I think that the first new data actually raised more questions than they answer, right? Even on the spectroscopy, it maybe goes in one direction, but in spectroscopy, in scattering, I wouldn't say that. But there are really many new experiments on their way, and they are really orthogonal in their approaches. So we will really corner the puzzle, and it has no way to escape. At least I don't see one right now. Might maybe say something else in 10 years. But really, these overlaps in the different fields in physics are really rare, and it was really something special to be part of that. And whatever the resolution is, we will certainly have learned a lot, even if it's only how to do these experiments or how not to do these experiments. And that I can only thank you all for listening. Actually, there's one correction from Michael. Hi, Michael. You're of course right. That's not at JPark. So ULQ2 is not at JPark. It's at ELF in Sendai in Japan. So we are happy to answer any questions. I think there was one question about using taus.
Yes, actually, sorry, Jan. It was a question from Maurizio Prisco, who was very curious to know, since nearly the very beginning, if one can use the tau particles instead of the muons for exotic atoms. So I leave you to answer that.
Yeah, I guess from the atomic physics side, the answer is unfortunately no. The fact is, the simple fact is that the tau does not live long enough. So you cannot produce a tau and make it that it merges with a proton and make tauonic hydrogen, and then the cascade takes picoseconds through the atom. So these exotic particles are captured into highly excited states, and then it takes pico to nanoseconds for this particle to fall down, and the pion lives only 200 femtoseconds, so it will not make it to the state, and you cannot shoot a laser at it. So that is unfortunately not possible. So the muon is really the sweet spot. It has exactly the right lifetime for us to do the experiment and exactly the right mass, but it's unfortunately the only one where we can do these measurements. You can use antiprotons, you can use kaons and pions, but with that there's a whole series of other measurements done at CERN and at PSI, and you learn fascinating and interesting things, but not at the moment about the size of these nuclei.
Yeah, for scattering, the answer is similar. You can do tau scattering if you really want to, but you have to give it enough momentum that it lives long enough. And with that, it's very hard to scatter with such a low momentum transfer that you can actually get the radius out. And just because it's so heavy, it's also not super easy to produce in the first place.
So I don't see other questions. I see, however, thanks from our public for your very nice and exciting lecture on this really important item. I mean, how big is the proton? It's, I think, one of the very fundamental questions we can ask about nature, about ourselves, and about how the world actually is made of. So I wish you a lot of success with your experiments. I really would like to host you again, maybe in a couple of years or so, when you might have agreement or even more disagreement, now seeing that the precision is increasing. And so Jan and Randolf, we wish you a lot of good luck in pursuing this really, really fascinating type of research, which shows that actually physics, independently that you do particle scattering, atomic physics, in the end, it converges towards learning how nature works.
And may I add, it is also complementary, because we learn from each other. We cannot analyze our data without the input from electron scattering, and electron scattering will eventually, when this problem is solved, be able to use our precise form factor, radius, whatever it is then from atomic physics, to improve the fits of the form factor. Yeah. So it's not a fight, it's a collaboration.
Absolutely. It's we are used to work in these collaborations, which are actually kicking us to go farther and faster. So once again, thanks to people from Germany, from France, from United States, from Italy, of course, from all around the world who are watching us, and just give us a hint, where are you connected from from now I see it's, France and Mainz and Italy. Thank you very much.
Yeah, thank you very much for the opportunity.
Thank you, thank you. And with this, if you share my slides once again, please. I would like also to thank a lot from the Frascati National Laboratories staff, Susanna Bertelli and Deborah Bifaretti, who you don't see, but they are behind the stage, actually ensuring that everything went fine, so that the Educational and Communication Office from Frascati National Laboratory continue to watch us. I remind you that this lecture was organized as a first kickoff lecture within the public lecture series of this beautiful European project, Strong 2020. If you want to know more, or if you want just to keep being informed about our initiatives, just connect to this website. You see it here. And we are now planning and scheduling the second lecture in the series. So we would like to have you here with us for probably by end of January or so. So this was the first lecture. And once again, thank you, Jan, thank you, Randolf, thank you, European community, and thank you, Frascati National Laboratories, from providing all the technical excellence support. So bye-bye to everybody. Thank you for following, and have a nice evening or day.
Thanks.
Or
Bye.